for universal out. The first, and easiest, rule we examine is universal elimination, universal out, for short. As its name suggests, it is a rule designed to decompose any formula whose main connective is a universal quantifier, that is, x, y, or z. The official statement of the rule goes as follows. Universal out O if one has an available line that is a universal formula, which is to say that it has the form VFV, where V is any variable, and FV is any formula in which V occurs free, then one is entitled to infer any substitution instance of FV. In symbols, this may be pictorially summarized as follows. OVFV. Fn here, 1V is any variable x, y, z. 2n is any name AW. 3FV is any formula, and Fn is the formula that results when n is substituted for every occurrence of V that is free in FV. In order to understand this rule, it is best to look at a few examples. Example 1 xfx. This is by far the easiest example. In this V is x, and FV is fx. To obtain a substitution instance of fx, one simply replaces x by a name, any name. Thus, all of the following followed by O fa, fb, fc, fd, etc. Example 2 y Rick. This is almost as easy. In this V is y, and fv is Rick. To obtain a substitution instance of Rick, one simply replaces y by a name, any name. Thus, all of the following followed by O Rack, rbk, rck, rdk, etc. In both of these examples, the intuition behind the rule is quite straightforward. In example 1, the premise is that everything is an f. But if everything is an f, then any particular thing we care to mention is an f, so A is an f, B is an f, C is an f, etc. Similarly, in example 2, the premise is that everything bears relation R to K. For example, everyone respects K. But if everything bears R to K, then any particular thing we care to mention bears R to K, so A bears R to K, B bears R to K, etc. In examples 1 and 2, the formula FV is atomic. In the remaining examples, FV is molecular. Example 3 xfxgx. In this V is x, and FV is fxgx. To obtain a substitution instance, we replace both occurrences of x by a name, the same name for both occurrences. Thus, all of the following followed by O fa ga, fbgb, fcgc, etc. In this example, the intuition underlying the rule may be less clear than in the first two examples. The premise may be read in many ways in English, some more colloquial than others. R1 every f is gram, R2 everything is gram if it's f, R3 everything is such that if it is f, then it is g. The last reading R3 says that everything has a certain property, namely, that if it is f then it is g. But if everything has this property, then any particular thing we care to mention has the property. So A has the property, B has the property, etc. But to say that A has the property is simply to say that if A is f then A is g. To say that B has the property is to say that if B is f then B is g. Both of these are applications of universal out. Example 4 xy rxy. Here, V is x, and fv is y rxy. To obtain a substitution instance of y rxy, one replaces the one and only occurrence of x by a name, any name. Thus, the following all followed by O y ray, yrby, yrcy, yrdy, etc. The premise is that everything bears relation R to something or other. For example, it translates the English sentence everyone respects someone or other. But if everyone respects someone or other, then anyone you care to mention respects someone, so A respects someone, B respects someone, etc. Example 5 xfxxgx. Here, V is x, and fv is fxxgx. To obtain a substitution instance, one replaces every free occurrence of x in fxxgx by a name. In this example, the first occurrence is free, but the remaining two are not, so we only replace the first occurrence. Thus, the following all followed by O fa xgx, fbxgx, fcxgx, etc. This example is complicated by the presence of a second quantifier governing the same variable, so we have to be especially careful in applying O. Nevertheless, one's intuitions are not violated. The premise is that if anyone is an f then everyone is a g. Recall the distinction between if any and if every. From this it follows that if A is an f then everyone is a g, and if B is an f then everyone is a g, etc. But that is precisely what we get when we apply O to the premise.